Okay, we're gonna do B, but let's write out the property. That special property is limit of psi over theta or theta over psi of theta. Okay, first of all, it only works with the psi. Change that to cosine, you don't have that property. You don't have that property with tangent. Okay, so only psi. And second thing, you see that's an angle. So if it's 2 theta, down there has to be 2 theta. Up here, if it is 3x, down here has to be 3x. Okay. So we just try to pop it down like that. If it doesn't have, most of the time you only have the sine. You don't have the angle. You only have the sine. And yesterday, we tried to mimic that by popping up the 2 theta. Right, 2 theta, that's why we multiply by 2 theta, divided by 2 theta, then we can apply the formula. Okay, so how about this one? How do we do this one? There are multiple approach. Okay, there's multiple approach to do this too. I'll show you a couple ways, okay? At least 2 of them. First, there's also another trig identity. You can try to multiply and then divide, and then it's gonna show up the that identity. Then you cancel that, you make it equal 1. However, there's another way is when you look at sine here, you sine 2 theta over there. That's double angle. Anyone can recall the double angle in trig? Sine 2 theta, or sine 2 whatever the angle, right? 2 is 2 sine theta cosine theta, right? Actually, you don't have to write over there. You can keep writing here. There. Okay. What do I see? I see one side in the numerator, one side on the denominator, right? One side theta. Actually, if you cannot see it clearly, you can write out okay, sine square, right? Is sine times sine. Then cancel. 2 cosine theta. Oh, actually, limit. Okay, don't make that mistake, huh? Always carry the limit with you until you plug in. Do not drop the limit. Okay. If you have a plug-in, you still have to write in the limit. This part right here. Okay. What else can I do with this? Okay. Try to plug in, right? Try to plug in 0. Sine of 0 is 0. Yeah. Plug in 0 here. That would be 0, which is not good. We can have sine in the numerator, okay? But sine in the denominator, we make it 0, which is not good. You're gonna have undetermined, right? D and E. Then you want to get rid of that sine on the denominator. What do? Use the property above, right here. Oh, it's right here, exactly this one. You need a theta over sine theta. So right now I have sine theta. I need that theta to match with that, right? So I multiply by theta and then I divide by theta. Okay. By doing that, I'm looking at this bubble right there. That is 1. Okay. Then what else? Okay. You still have a theta on the denominator. You plug in again, you still have 0. How do you do with this? But this time you don't have sine anymore. So reduce the low a little bit already. You still have some theta down here, 0 down here. What else can you do? What else can you do? Okay, here's a trick. Remember yesterday we did a couple of techniques when we have undetermined like this. Undetermined, the zero in the denominator. What did we have? What did we do? What are the techniques?
Move the constant in front of the limit.
Yes, you can do that. Technically, yeah. That's one way to do that, okay? Number two doesn't matter in this situation. Some other techniques that we learned just yesterday. When you have undetermined in the denominator, you try to factor, right? You have a quadratic, you factor, you use x method. You have difference of square. You see a square root, you multiply by conjugate. Right? If you strip them already. And then if you have something really simple, you recall the graph, the thumbnail, the model function of that, right? Right? You know, x squared, parabola, hyperbola, and so on. Right? Absolute value and so on. This one, if I break it, or I'm not really break it, separate into 1 over theta multiplied by cosine theta. There. Split it out like that. Remember, yesterday we have the limit law. Limit of a product, you can split that into two limits. Limit of a product, yesterday, limit of f times g, right? Theta approach whatever, or x approach a equal limit of f times limit of g. Right? So that is two functions right there. F, g. So just break it and analyze it one by one. There. You can break a limit. If it's a product, if it's an addition, if it's a subtraction, you can split a limit. Okay, now it's much simpler, right? Theta approach 0, plug in 0 right here, you can do that, right? That's just 1. Right, plug in 0, cosine of 0 is 1. So this, the later part, is 1. How about this one? In order to know this, also from yesterday, how do you plot 1 over x, the hyperbola? What does it look like? 1 over x. If I have to draw that, a thumbnail of that, a parabola and hyperbola, a hyperbola, right? It looks like this. Approaching 0, okay, and then, this problem is good. This can buy everything you studied yesterday. Approaching 0, theta approaching 0 is approaching from the left. If it's written like this, if it is written like this, it is approaching from the left or the right. For both sides, right? There's no plus, there's no minus. So this indicating approaching from the left and right, right? Left and right. That means from both sides. 0 right here, approaching from the left, it go negative infinity. It stay beside that. Approaching from the right, go positive infinity. So therefore, approaching from both sides, it is D and E. They're not the same. So this is D and E. Technically, you have this thing. D and E, 2 times something that is not exist, times 1, right? What would be your conclusion for this product? Undefined. Is it? Yes.
Going back a little bit, before you multiplied the 2 cosine over theta by theta, couldn't you just write that as 2 cotangent theta?
Yes. The reason it's personal reason. I detest cotangent. I don't like cotangent. I like sine, I like cosine. Tangent is sine over cosine. Cotangent is cosine over sine. But bring it up, usually I limit it. I also want to limit you guys in terms of formula, in terms of properties to sine, cosine, tangent. Right? Because cotangent is just a reverse of them. So yes, you can analyze cotangent, but not a lot of us familiar with the cotangent. Yes, another direction is right here. Instead of multiply that is just 2 cotangent of theta. And yes, you can analyze the plot of cotangent of theta around 0. But anyone know what does it look like?
Like an asymptote.
You have an asymptote. It's gonna look like this. It's not really familiar to your eyes, to be honest. There you go. There's that round 0. That is 0 right there. On the left you go down, on the right you go up. Yes, you can conclude D and E right here. But if you want to go that way, you're gonna have to be familiar with the cotangent. Okay. That's also a good option to pick. All right. Pick one. That one direction. Another direction. Okay, technically we have 2. We just had 2 already. Another direction is, we're not finished to the end, but I'm just gonna give you the idea. Is you have this, right? Sine of 2 theta. Now you know the idea. Is you're gonna multiply by 2 theta divided by 2 theta to have that. Right, that's the numerator. And then the denominator, sine square of theta. Right. Okay. For the numerator, I do this. I multiply by 2 theta divided by 2 theta. Too much. That 2 theta. But for sine square, the property is a spherical property. Only have sine theta over theta or theta over sine theta. Just first degree. There's no square in there. I see a square here. I can still use that formula. What can I do? I can write like this. So therefore, the angle in here is basically that. Theta square. That by theta square. Okay. Combine these two. That is 1. So I have theta square here. Okay. So that is another approach. It will eventually end up to be 2 over theta, which is D and E again. If you do the honor simplification, okay, this is 1. This is also 1. Right. Using the property, this is 1. You only have this divided by that. Number 1, just multiply by number 1. This 2 theta divided by theta squared. The theta cancel with this theta. 2 over theta. This going to 0 from both sides. It's going to be D and E. Okay. So yeah, 3 approaches. The more you learn later, when you learn in 3.7, after you learn derivative, you're gonna have a 4th option. You take the derivative of that. Okay. Use the hospital rule. Okay. Some of you may find that familiar. Okay. All right. Moving on. Yeah. This note is incomplete, like 90% complete. Stop at number 4, section 4, limit of trigonometry. There are a 5th one, so it's not in there. So you may want, get write on some other space, or make some space for this one. The 5th one, which is also very common. Okay, it's called just squeeze theorem. It's very short. Squeeze theorem, aka sandwich theorem. It has that name too. Informal name of this one is sandwich. Squeeze theorem. Sandwich theorem. Okay. It involves trick. Okay. It's very simple to understand. If the theorem is like this, if f of x is less than or equal to g of x, so one function is smaller than another function, then the limit for both of them, the limit of f of x, when x approach a number, is also less than limit of the other function. Okay. very simple. If one this is less than this, then you put limit in front of both of them. This also stay consistent with the inequality. Okay. So that's the theorem. Okay. If we upgrade the version, if we upgrade that, if we have 3 of them, 3 functions, and they are lie in an order that f is less than g, less than h. Okay, so now 3 functions. Then the inequality stay consistent too. The limit of f of x less than limit of g, and so also limit of h. Okay. So this is right here. Let me box this. Okay. So Swiss theorem right here. If you have a function that's greater than 1, and here less than this one, okay. Why do we use it? Sometimes this function right here in the middle look complicated, extremely hard to find. Huge, big function look nasty, right? Ugly. But somehow we know that that function is bigger than something that is simple enough for you to find limit. Over here also that function is less than something that is also easy to find the limit. And you don't have to find the limit of this one. You just need to find limit for each one of these two. And you squeeze that one in the middle. That limit is going to be equal both ways. Let's do that with an example right away. You have, okay, let's do an example. I'm going to give you something that is not easy to find directly. None of our technique that we have so far work with this. Okay, so limit of x squared sine of 1 over 3x. Okay, it's really erratic, you know. Really, the behavior really unpredictable when it approaches 0. Remember, limit is about behavior. So the behavior of this function is really erratic around 0. Really hard to plot. Really hard to use algebra because 1 over 3x is inside side. So you don't have a lot of leeway to play around with 1 over 3x. Okay. So therefore, finding limit of this one right now we don't have enough tools to do that. So what do? We utilize the idea. We utilize the idea that psi. Okay. Here the solution. We utilize the idea of psi of whatever the angle is on way between psi of, okay, if you use calculator, you put in psi of 1, psi of 2, psi of 3 theta, psi of 3 pi over 4, pi over 2, whatever the value, you plug in that theta, that psi. If you notice, it's on way between a certain number. That's also the limit of psi. -1 and 1. Remember the unit circle? This is psi, right? Psi is nothing more than a clock, sine, cosine. Technically, that needs some say. Psi is nothing more than a clock. Whatever the value is 0, pi over 6, pi over 4, pi over 3, pi over 2, right? Pi, 3 pi over 2, 2 pi. You keep rotating that clock, right? But whatever the value you plug in, the value that project down to this, right? Actually project down to this axis is only between 1 and -1, right? So psi of whatever the angle between -1 and -1. Therefore, again, whatever the angle, That is the angle in this case. Still have to obey the rule, same rule. Right. Okay. We try to mimic that one over there. That one over the top one over there. Okay. We are this one. This is the one in question. Right now we have that between negative 1 and 1. Okay. Multiply boss. We need this one. The missing piece is right there. X squared. So how about we multiply x squared? 3 side. Okay. Here. Multiply by x squared. Okay. We just set up the squeeze theorem. Okay, I'm going to zoom out. Look at this very last slide down here, and the very first slide up there. You see the sampling. F, G, H. All right. F, G, and H. Now, if we put the limit, we can follow this one. Put the limit in front of each one of them. Limit in this case, x approach 0. Okay, so put that limit. Negative x squared. There you go. All right, squeeze through. Okay. We are looking for the answer to this. We don't know. But do we know this? Which is? What is what is it? Which is 0. Plug in, right? Just a polynomial. 0. You have something that greater than 0. You have something that greater than 0. You have a number that greater than 0. Also, that same number is less than 0. What is that number? What that number is? 0. You see the sandwich? You see how you squeeze that number in the middle, right? This has to be 0 by squeeze theorem. There you go. That is the answer. So far good? Okay. So you're gonna see this squeeze theorem in the homework. That's why I brought it up. Okay. Let's say we close out 1.4. Okay. Let's move on to 1.5. Okay, 1.5. Any questions so far? Okay. 1.3, 1.5 here. Okay. All right. Oh. Okay. Okay. To continue with limit, we're supposed to learn. Okay, first chapter we learn about everything we learn in the first chapter is about limit. But to keep going with the order technically we learn different techniques to take limit. We learned a few of them already. Plug in, factor, different of square, conjugate, trig, squeeze theorem. Learn a few of them. To moving on with the new order techniques, we need to know one property, very special property. And this technique only applies to a certain kind of function. That function has to be continuous. That's why we're going to take a detour to the concept of continuity. Okay, so continuity. So what does it mean by a function that is continuous at a number seem really simple, right? This is sound really simple, right? Right? Continuous, just smooth. You don't have hiccup. You don't have open. You don't have jumping. So that is continuous. So, but in mathematical language, continuous is when you have limit of f of x when x approach a number equal f of a number, f of that value. If you recall yesterday, okay, whatever the function we were able to plug in, they are continuous, right? And then there are some functions when you plug in, you have 0 in the denominator. Those functions are not continuous, right? So if a function, in other words, in the mathematical language, a function that is continuous, that means when you find the limit, you are able to plug it. There you go. You can plug it anywhere, right? So that's continuous. And to satisfy this condition, okay, there are 3 things must be satisfied. First, the left hand side, the limit f of x when x approach a is defined, aka exists, right? Okay, exists or is defined. And then the right hand side, f of a is also defined and exist, the same thing. Okay, and the third thing, left hand side and right hand side, they have to be equal each other. So left hand side has to be equal right hand side. Okay. All right. So let's do a simple example. I may draw a curve like this. Most of the time I'm gonna do very simple curve, right? Here, let that open at around 3, okay? X at that position, maybe another 3, okay? And then I go down here, maybe pick another one, -1. I jump to here, 7. Okay, maybe here, 4. Okay. Okay. So this is more theory. This there's not a lot of calculation. Just observing and analyze the problems. Okay. Analyze the continuity at 3. Analyze the continuity at number 3, at x equals 3. So that is a question. Analyze continuity okay. Right. Clearly, first of all, we have to establish this. Clearly, everybody can see that it is continuous, right? But we cannot just say by looking, it is the continuous, right? Now we learn more math. Okay, we have to write our explanation using math language, right? We cannot say, looking at this, is it is continuous as 3? Clearly, no. We have to use that idea over there, okay, to prove that, okay, if it is continuous, it cannot satisfy any equals to 1 over there. Okay, so what does it mean by continuous again? Just that. Can you plug in as 3? Okay, you can. If you can, are they equal? Sure. So the limit here, limit when x approach 3 from both sides, are they equal to f of 3? So let's analyze that. The 3 condition. First condition, 1 by 1. Actually, I'm going to do it over here. Okay, 1 by 1. Because I'm going to do 7 too. Okay, the first one. The limit when x approach 3 of f of x. What do you think? Now it's easier. I'm not going to write out left hand side, right hand side. You can see right now, right? It equal. Huh? Don't exist. DNA clearly. Left go to 3, right go to -1. the second condition. Okay, first condition. It says the not exist. Okay, there you go. That is enough to say it's not continuous already. Okay, second condition. F of 3. F of 3 equal -1. Okay, the second condition satisfied. Third condition. The left hand side, is it equal right hand side? That means, is this equal this? Nope, right? Okay. So among 3 conditions, 2 of them you already failed. Right? You failed the third one, you failed the first one. Therefore, it's not continuous as 3. That's how you write out, that's how you actually show the, prove the continuity. So therefore, this continuous at x equal 3. Okay. Okay, maybe this is it 2 right here. That is 2. There, okay, so to show you that. Okay. Now, how about you? Can you try that? Can you try analyze at x equals 7? Try that. Okay. Very simple. Write out that. Okay. Check that. You have to satisfy all 3 of them in order to be continuous at a number. All 3 of these. How about x at 7? First, find limit when x approaches 7 from both sides. Second, find f of 7. Third, are these 2 equal each other? Okay. And of course, before you do this problem, by looking, yes, by looking, not continuous, right? There's a hole right there, not continuous. But how do you actually prove it? Okay. So I need 3 things. First, how much? 2. Second, how much? 4. Okay, so this check define, that means you're able to have an answer. That means define. Third, equal or not equal?
Yeah, equal.
2 and 4. Equal or not equal? That means this one. Left hand side, this is the left hand side. Right hand side is this. This is the value of left hand side right here. Right hand side right here. 2 not equal 4. They're not equal. One of the, yes.
How would it be right hand side equal to 4? I thought it was talking about like the general, like as x approaches 7 from the left and right. If that's not true, like from either one, wouldn't the limit of x approaches 7 in general not be true in general? Like if they don't equal, then
Okay. The right hand side, when I say the left hand side, is not of this equation right here. Left hand side is of this property right here. This definition right there. The left hand side is this one. This thing. Find the value of this one. That you call that the left hand side. Okay, so when you do that for this problem, that left hand side is this, right? That equal 2. The right hand side is f of 7. That equals 4. Okay. Let me write more for you. Okay,
So you were just referring to the equation you gave us, the definition?
the definition. Okay. By definition, you need this. Okay. Okay, right? By definition, we need this to be true, to be continuous at 7, right? By definition. Then if this right here, this equal right here, what is the left hand side? This, right? This is the left hand side, right? How much it is? 2, right? 4. Are they equal to each other? They are not equal to each other. Okay, but you need that to be continuous as 4. But it's not. Therefore, not satisfied. There. Okay, you can also write it this. Of course, you can also write it this. But usually I break it down into 3 conditions so that you can easier to analyze. Yes, you can write it this. It's just one single line.
Why on the right hand side is there approach 4 and not 2?
Oh, f of 7. Okay. First of all, when you find a value of a number, right, you should go straight up or down. You find the close, right? You don't want to locate the open, right? So 7 right here. You go up. You hit this one. This. Do you pick that?
No.
No, that because it is open. So therefore you don't pick number 2. Right? It's not equal to. You keep going. You see that? Close. That is defined there. That is 4. So therefore f of 7 equal 4. Okay.
And f of x always equals the right hand side? Not necessarily.
F of x in this context, in this definition, yes. F of x will on the right hand side. Yeah. But it defined or not, it's not always true. Sometimes it's going to be undefined. If I erase, for this problem, I erase that dot, then f of 7 will be undefined. If I erase that, you still have a whole line here. Right? So f of 7 is undefined. Okay. Good. Any more questions? Keep going. Yeah. All right. Moving on. Now the definition. So, the first definition we had was when a function continues at one point, one number, 7 or 3. Now, okay, let's see if you continuous right here 3, right? You continue at 7, right? Let's say make an example. You also continuous at 4, continuous at 5, continuous 6, continuous everywhere in here, 4.4, whatever that number. Then what can you say? You continuous on the whole interval, right? Same idea. You just expand it out. If you continuous at one point and you are able to locate the next point also continuous, and they are continuous. Keep going, right? Continuous at every point. You do that thing. You do that definition. You satisfy 3 conditions. 3, 3.1, 3.2, 3.4, and so on the way to 4, 4.1, 4.5, and as far as you can go. If you're able to expand one point into a whole interval, and you're able to tell that at every point I am continuous, then on that whole interval, I'm also continuous. So that is what it means in this definition. Continuous on an interval, so it continuous on every point in that interval. Really, really simple notation. But apply that to this function. show that this function is continuous on that interval, negative 1 to 1. Okay, negative 1 to 1. Again, 3 conditions. First, but this time we do it on an interval. First is limit when x approach. Okay, I leave it blank here. I'm gonna come back. Okay, 3 conditions. First, limit of f of x. It has to be exist. Okay, just write out the idea. Okay. Second, f of x also is. Sorry, I put it here. 3. Okay. If I put the left hand side, right hand side is too complicated for you. How about I write it this 1 equal 2. There. So let's make this one to be equal to this number 2. If they exist, they equal each other, then you satisfy with that one. Okay. Unlike the first one, is at one point. This time we're dealing with a whole interval. The first example, we approach 3, so we say the limit when x approach 3. When we analyze 7, we put 7. Okay. This time, it's in whole interval. We don't know which number is approached. Then how do we actually write something that represents that idea? We're approaching a whole interval, not just one number anymore. Okay, so we just pick a random number, an arbitrary given a letter, approach A, and we say that A inside this interval. There, right? Instead of saying negative 1, negative 0, negative 1, negative 0.5, 0, and 0.5, and 1, and so on, unlimited numbers inside that interval. Okay. So how about we just say give it a random. But we say that, okay, that random number between negative 1 and 1 to 10, there you go. Also this one, again, this one exists, but also inside the interval. Last example, it was f of 3 or f of 7. But this time, f of something, that is f of a, also between negative 1 and 1. There. Okay. Find both of them. If they equal each other, then you have a continuity on the whole interval. Okay, one by one. Limit when f of x, when x approach a, f of x is this, plug it in. Okay. A, it's just arbitrary. Okay. But you look at the function. You're going to ask yourself, can I plug in? Yes, right? You can plug in. It's not 0. It's not something we are looking. You cannot plug in. There's only one time you cannot plug in is you have 0 on the bottom. Only when you have 0 on the bottom. That is strictly, and you cannot plug in. And you have to analyze. But this time it's just one single line, just a polynomial, just rational with square root. Nothing harm you. Okay, so just plug in normally 1 plus 1 minus a squared. But just keep in mind that a is between negative 1 and 1. There. You can plug in. You're not plugging 0. Even if you plug in 0, nothing happens. Okay. So okay, another question for you. Then you have this. It equals this. And it equals this. So is number 1 defined? Is number 1? Is it defined? Is the limit defined? That means it exists some number. As long as you can come up with some number, then it defined. Undefined, that means you have 0 in the denominator. Is it defined in this case?
No.
Yes, it is, right? A, anywhere in here, you can plug in here, it gives you something. So it's defined. So that means the first one check is this and define. So I mark this, check that. How about f of a? F of a, you plug in f of a, or just plug in a, right? Also define and exist, right? If a between -1 and 1, okay, therefore this also exists. Okay. Number 1 get me that. Number 2 also get me this. They identical, right? 1 and 2 equal each other. Third. Therefore, my conclusion will be f of x, whatever that f of x is, continuous on -1 and 1. Okay. All right. Any question? So basically, at one point, but you just try to open that into an interval, right? Good. Okay. Now let's practice some sketching. With that idea of continuity, can you sketch 4 graphs? Maybe I'm gonna have you with one of them. Okay. Do 1, you do 3. How about that? Okay, sketch 4 of them, so maybe draw an x-axis here. Okay. That f it is continuous at 4, but also continuous from the left of 4. Okay. Continuous as 4. It doesn't say anything about on the right of 4. Right? First of all, that's one thing we know. Okay, discontinuous at 4. So draw a curve that is continuous at 4, but also continuous from the left of 4. Okay, so maybe first one. So that's mean. Okay, I'm gonna draw first. I'm gonna explain later. Okay. There you go. Right. Look at 4. Look at 4. Clearly. Discontinuous. That's all right there. Discontinuous, right? There's no close on this. On the level 4, right there, continuous. It doesn't say anything about the right 4. I can draw something on the right, whatever I draw is okay. That's still correct, right? Okay, try. How about you try the other 3s? Okay, try it. Technically, the moment I put another line like this, that is another option already. Right. Right. Okay. Try that. Okay. Moving on. Yeah, moving on. Okay. Some property with the continuous function. Okay. Let me mention. Okay. Similar to the limit. This one here, you're gonna have a bunch of property like this, but without a limit. So, if two function f, g, both of them continuous at a number, at a or in an interval, okay, then the addition, both of them also continuous, okay, Really simple. If you have x, that clearly continuous everywhere, right? That is simple. X squared, right? So each one of them continuous. I know for sure that function x plus x squared, I'm not going to analyze anything. I know for sure that it is also continuous, right? If you have addition, you should have subtraction. Okay, you also have product. You also have division. As long as g of a is non-zero, when you plug in 0 have 0, then you can also continue. Okay. And the last thing, c times f also continuous. C is a constant. Okay. If I know x is continuous, for example, again, this one, x is continuous, then 3x also continuous. Right. You multiply by a number. That basically divided by a number, right? But I write that in terms of multiplying 1 over 3. That basically x divided by 3. So also continuous. Okay. All right. Straightforward. Some function that automatically continuous everywhere on its domain. Okay. So when you're able to name this kind of function, give them a name. Able to name them, like I said. If you have a parabola or linear, okay, if you're able to name them, and you can say that it also continuous without doing on the proof. Okay. Can you think of some function? Maybe one. Some function that automatically, by default, continuous everywhere on its domain.
Cube root.
Cube, yes. Cube is continuous, but more general than that. Okay. X squared is a parabola. Okay, quadratic. Cube. Okay. They still specific to these two functions. The names. I'm talking about the name. The cubic and the quadratic. They are specific for those two. All of them continuous, right? But they don't have the name for the 5 and the 4, right? But they have the name for all of this. Or exponential. We're gonna study that in chapter 4. Exponential is backward. The x has to be in the exponent. So exponential is different than whatever we are trying to find. The x in exponent. The base is a number. The one that in the circle, the exponent is a number. Okay, you can. Then back to the question. All of this, what are they? Huh? Polynomial. Polynomial. Rational. As long as it's in the domain. Okay, rational also good. A root function, square root, cube root. A fourth one. I'll let you think about the fourth one, the final one.
Absolute value.
Absolute value is basically a linear function. It's one case of this one. It's the first degree. Absolute value is a special case by itself. It looked like this, right? It looked like this because the left hand side was bent upward like that. It's basically x like this. But if you put the absolute value, then this tail right here bend upward like that. Originally, absolute value is just x. Okay, and x no more than x to the power 1, right? X to the power 1 belong to this, right? 1, 2, 3, 4, 5. X linear function is a special case. In other words, this is a special case. This is a special case. A polynomial is a linear, a line. Simple as That's why it has the specific name is linear, quadratic, cubic, and so on. But they are in the same family. Like that.
What about trigonometric function?
Yes, that's the one. Remember sine, cosine?
Sine, cosine.
Yeah. The sine wave, they usually say the sine wave. Just keep rotating like this, right? Up and down, fluctuating up and down. It's always continuous. There's no hiccup, there's no interruption. But for sine, cosine only, not tangent. Alright, cosine. Very smooth, very continuous. Okay, so when you see those functions, you're able to name them. Oh, sine of 3x. For example, show sine continuous by default. It's a trig function. You don't do anything. It's default. By default, it's continuous everywhere. Right. There you go. Okay. All right. For which value of k, so find k in other words, find k that make this function a function that you use the bracket like this. You know, what do you call this kind of function? You have a bracket like this.
Piecewise function.
A piecewise function. Yeah, piecewise function. It's separated into pieces. That's why it's called piecewise function. So f of x is just a piecewise function, okay? All right. For which value of f of x, for which value of k, that f of x is continuous everywhere. When you say it's negative infinity to positive infinity, I usually don't say that. It's another way to say it's everywhere, right? All the way from the left, all the way to the right, everywhere is negative infinity to positive infinity. Okay. All right. So for which value of k, so that function is continuous everywhere. Let's start with the solution. Recall. How do we? Okay. So it's piecewise at 2. Technically, it's cut up at 2. In other words, I'm just gonna draw roughly like this. When it's less than 2, maybe it's not correct, huh? Maybe it's look like this. There. And then greater than 2, it look like that. Right? I'm just trying to make an example, even example. It's not corresponding to these two. Clearly, on this picture, this thumbnail, very discontinuous at 2, right? Then if you're able to, like a visualize, you're able to imagine this is a touch screen, able to move these to the ground, everything around. How do you move this? So that is continuous at 2. What would you do? If you're able to, move something in here.
The constant.
You constant. You can 2.
And like the second function, like if you change the +4, you would write it down to the 2, and then you could bring it.
Yeah, the constant. So I did okay. Less technical, more. How about basic than that? More basic than that. You're able to move these two. If you're able to move them, how would you make it to visualize it so it can be continuous? Let's say. Oh, actually, I can move it, right? Yeah, I'm doing. I have touch screen. I forgot. Okay. If I move this, where would I put that so that it's continuous at 2? Right? By doing that, it's continuous as 2, right? But right now it's not. Okay. Right? So in other words, I just have to move. By doing that, right now, this one, the limit of this function, when I approach it from the left of 2, it equals some number down here, right? The limit approaching from the right of 2 equals some number up here. They are not equal each other. When the action that I move this one down here, what did I do to the limit? I make the limit from the left equal the limit from the right, right? Mathematically, that is what I did. Visually, that's what I did. But if you want to achieve that thing, mathematically, you want to have the limit from the left equal the limit from the right of this function, right? So that is how we start the problem. Find limit from the left, find limit from the right. Make them equal each other. There. So limit. So you want the limit of f of x when x approach 2 from the left equal limit of f of x approach 2 from the right. You want them to equal each other. So where in there the k gonna pop up, you're able to solve for k. Okay, so one by one. First, analyze the left hand side. Okay, find this. Okay, approaching 2 from the left of f of x. This is my f of x. I have two functions inside this f of x. This and this. So if I approaching from the left, which one do I pick? Top one or the bottom one? The top one, right? Approaching from the left, right here. That means left of 2. Left of 2 is less than 2, right? Left of 2, less than 2, less than 2. I have to use this. Okay. It's not a rational function or anything awkward. It's just a polynomial, so you can plug in. Okay, 3, 2, q minus k times 2. Simplify that. 8 times 3, 24, minus 2k. Okay, so 1. This is 1. This is 2. Okay, now number 2. Limit when x approach 2 from the right, f of x. This time I pick the right hand side. I mean the bottom. Because it's greater than 2. And again I'm gonna plug in. K2 square plus 4, which is 4k plus 4. Okay. And remember, in the beginning, I said I want number 1 equal number 2. Number 1 give me this. Number 2 give me this. Right. To be continuous at 2, I want this equal this. One equal 2 if and only if 24 minus 2k equal 4k plus 4. You just have a basic function of k, right? So for k, (6k), right? This one over here, yeah, just plus 2k, minus 4 plus 2k. So 6k equal 20. K equal 20 over 6, 10 over 3. There you go. So because when you have k equal 10 over 3, then this will equal this. And because this originally is that left hand side limit. This originally is the right hand side limit. When k equal 10 over 3, you have the left hand side equal the right hand side. Therefore, you have continuous as 2. Okay. Any question? Okay. All right. Okay. Next thing we learn: composite function. Composite function. basically function inside a function. Function inside a function. Okay. F of g. This is read out as f of g. Does it? Okay. Meaning that you plug a function inside another function. Okay. So, okay. That f of x. If I ask you to plug in 1, I don't think you have any problem, right? Right? That's a 3. That what if I ask you to plug in g of x? So you plug in literally, you bring the whole g of x to plug in. What is g of x? Right? You plug it that in. Okay. Where do you plug that? Negative. This is g of x. G of x should go this way. You bring this thing, you plug inside the f. The f is this. Where do you plug? Look right here. Same like how you plug in number 1. See, you plug in there. This time you plug in 3 over negative 2 over x squared. This is where you plug in, right there. Inside the x. The x is x squared. Now you play that with negative 2 over x. Okay, simplify. Don't forget the parentheses. Because with parentheses, that negative 2 squared become positive 4. Okay. All right, this from pre-cal. How do you reciprocal this? But where which number gonna go on the top? Which number gonna go on the bottom? So 3, 4, and x squared. Okay, if I have to write that in just a fraction. Okay, now there are 3 levels, right? 3, 4, and x squared. I just want to write some 2 things. Pre-cal. Which one goes up? X squared. Go to the top. How about number 3? Top. That leaves number 4. Okay. Okay. So you have that, basically. Even better. Don't think that. Okay, if you write it out, it may confuse you. You think that is rational function. But 4 is a constant. 3 over 4 x squared. In other words, it's like that. That's basically a parabola. Right? Parabola. Okay. What is the domain of the composition function? The composite function. Domain of this, which is domain of that, which is domain of this. Domain of that. Domain of this. The reason I write out in terms of a parabola, what would be the domain of that? Domain of a parabola?
All the numbers.
On a number. Yeah. Parabola. What's that? Everywhere. So the domain D is just negative infinity to positive infinity. Or you can write that it's just R, right? Or everywhere. Is it T-minus everywhere?
Yeah.
Not really. Because this is a composite function. If originally by itself, f by itself is this, then yes, that is polynomial, quadratic, continuous everywhere. But this one is not the same with this. F it is. This one was born from these two. In other words, this one has shares some DNA of these two. Right? That's a composite function. That is one limit of composite function. This one has the limitation of these two. Right? And among these two, the g of x, both of them technically, right? g of x. X inside the g of x. That x cannot be 0. Therefore, this one inherits that property to g. Therefore, this one also continuous, yes, everywhere except number 0. Okay, so that is one thing about composite function. Not the domain is still satisfied. You can still plug in 0 here, you can still get number. But if you plot that one, if you actually use the calculator to plot, computer to plot the composite function, that one, you're gonna see it is continuous at 0. So continuous everywhere? No. F of g is discontinuous. Continuous. This one from that. Even though this one equal x squared, a parabola. But that 0 comes from this. So basically you're dealing with regular function, but you be a little bit more analytic, okay? A bit more sensitive with the composite function, okay? All right. Any question? Okay. Carry on. Okay, we have intermediate. Okay, let's finish this one and then we have a little bit break. Okay, intermediate value theorem. Okay. Okay, IVT, usually called in short, intermediate value theorem, IVT. Okay, what does the theorem say? If a function is continuous on a closed interval, first of all, closed interval. Notice, right there, actually there. If it continues on a closed interval, then f for every value m, so you handpick any number randomly m between f of a and f of b, okay, there exists at least, okay, the correct word is at least one value c such that f of c equal m. Okay, sound really tripping, right? Sound really tripping. Theorem usually they try to make on the word, make the sentence sound fancy, right? That is the job of theorem. Try to confuse you. But in plain English, IVT, this is what I want you to actually memorize. IVT means that a continuous function cannot skip value. That's it. That's what we actually been studying so far. A continuous function, you cannot have a hole. Skip, that means you have a hole. Skip, that means this, oops, there. Right? You don't do that with a continuous function, right? You cannot have this. That is what IVT trying to say. A continuous function do not skip value. You go here, jump there, no. You cannot do this, and then you jump up here, you can do this. Right? That is not continuous. So in other words, continuous function is a smooth curve. That's it. Okay. Then, if it's so obvious like that, why do we study? Why do we need that theorem? Using scenario, it is used to determine if there's a root on an interval. Okay. It's really powerful, really obvious, but also very powerful at the same time. Before we go into the example, what is a root?
So 0?
Yeah, it's 0. A 0, a solution, right? A 0 or a solution of a function. But geometrically, there's one more name. There's one more name for a root in terms of x-intercept. This is what I'm going to pay attention to. Okay, so in other words, IVT determine there is an x-intercept. As long as your function cut the x-axis somewhere in there, at one point, that point is your solution, right? Right. So, if I have this, a function like that, clearly the root right here, I call that C. Clearly the root right there, right? That is your root, that your x-intercept, that is your solution. Okay, I also see that this function, smooth, very continuous, no disruption anywhere, no hole anywhere. Then how do I apply IVT to show that this one has solution without actually finding that solution? I know that, okay, I'm gonna have a solution. Using IVT, I pick a point in the beginning. A, I pick another point at the end. B, okay. What do you see? What do you see from this A and B? You don't know the value, but at least what can you tell from f of A and f of B? Let's say, what can you tell from f of A and f of B? Go ahead.
Sorry, F of C is somewhere in the middle of the two.
Yes, yes, C is somewhere in the middle, correct? But I want you to focus on f of A right here and f of B right here.
They're opposites.
They are opposite. They are opposite. If you, no matter what, you plug in calculator, this f of A is a positive number, right? This f of B is a negative number. So that's why IVT come in. If you able to find a value, you plug that value in your function, is a positive. You also plug in another value somewhere in there, is a negative. You have one over here positive, one negative. Okay, positive, negative over here. And then you try to connect them. You use a string, connect them. No matter how you connect between A and B down here, no matter how you connect them, it must cross this x-axis, right? Right. You cannot skip it. You can go over here, come back, right? No, you still cut over there. Right? No matter how you connect these 2 points, as long as one is positive up here, one is negative down here, in order to move from positive down to negative, or from negative back to positive, you have to cross the x-axis. And the moment you cross x-axis, you generate a root, you generate an x-intercept, you generate a solution. That's how you prove you have a solution in between A and B. Okay, good? So very simple. That's just theory. The application, very simple. This is your function. Use IVT to prove that you have a root between -2 and 0. What do? Pick a number. Pick 2 numbers in actually. One of them had to be greater than 0. The other one had to be less than 0. Okay. And that the first thing, okay, first, second. The third thing, you also have to show that, say something that f of x is continuous. Okay. This one easy. Technically, this one easy. This one should be the first one. To be honest, this one should be the first one. Is it continuous between -2 and 0? This function. Is it continuous between -2 and 0? Do I need to do anything? It's continuous, right? Why? Polynomial. Therefore, routing T. Continuous technically, not just in that interval, continuous everywhere. Okay. Pick a number. Now, also again, pick a number in that interval. Think. So that you can have. One of them is greater than 0, the other one is less than 0. In that interval, what would be your best? Okay, what would be your initial pick? If you're given something, what would you given a number? What would be an interval? What would be your initial thought?
0 and -1.
0 and negative. Actually, even better. These 2 numbers right here. If you're given an interval, start with those 2. F of -2, f of 0. Actually, let's see f of -2, Don't jump into. I'm not going to. Make sure it is radar. One of them is radar. One of them is less than. Okay. Negative 2 q plus 2 times negative 2 plus 1. What's that? Negative 8 minus 4 plus 1. Clearly less than 0. Negative 11. Okay, so negative 2 equal negative 11. So that should be down here. Is less than 0. F of 0, 1. Right? F of 0 is 1. Okay. So F of 0 equal 1. Okay, so if I visualize that, now I am able to visualize. Okay, F of 0, 0 right here. F of x, F of 0 equal 1. There, right, F of 0. I'm going to use this color. That is F of 0, dot. F of negative 2. Negative 2 is negative 11. Down here. Okay. F of negative 2 is negative 11. F of 0 is 1. And I know for sure guarantee that this function continues from here to here. So now I want to connect them. Because it's continuous, I'm able to connect them, right? No matter what I draw, I always cross here, right? At least one, right? You can do this. Right? Do you cross? Yes, you cross, right? I'm trying to cheating, right? Still cross, no matter how you do it, because it's continuous. Okay, you cannot escape the fact that you have to cross x-axis, at least one. So therefore, by IVT, f of x has at least one root in negative 2 and 0. Okay, they couldn't pick a better day to do construction, huh? Alright. Okay. Final touch. Why do I say at least? You can fluctuate up and down. You can do this. Technically, it could happen like this. There. Alright. It could happen like that. So, but for sure, at least one. Okay. Let's check 10s. And come back. Okay, keep going with this. 1.6.